now we will see in physics refraction of light, which is helpful for our polytechnic entrance test. Okay. At first, light we are having mainly two properties we have. One is about reflection of light, another one is refraction of light. Reflection of light takes place whenever the light ray incident on a surface which is an opaque surface, whereas refraction of light takes place when the light ray incident on a surface which is a transparent surface we are taking. Okay. When come to the case of these surfaces, mainly we are having two types we have. One is called a rarer medium, another one called as a denser medium. Now, we will see what do you mean by this rarer medium is. Okay. The term rarer. Rarer medium is a medium where we are having the density of the materials or the particles present in that medium, it is very less. Means the distance between the particles is more. Here we call that as rarer medium. In rarer medium, the density is less, that is. Best example you can take air. Here the dust particles or the air particles present, they are having more distance between them. That is why it is called rarer medium. In rarer medium, the light ray always moves with a greater speed. And when come to the case of denser medium, now here if it is a denser medium, in case of denser medium, here the molecules are closely packed or the particles are closely packed here. Best example for that is we can take for the case of glass or like water. Okay. So, in case of denser medium, as the particles are very much closer to each other, the light ray moves very slowly in this medium when compared to the rarer medium. Okay. So, rarer again we will see, rarer means nothing but here the particles which are having more distance, so that here the light can travel very faster. Best example is air. Whereas in case of denser, here the particles are very much closer to each other and the particles are very much closer to each other, closely packed. That is why in case of denser medium, the light ray is passing very slowly. Best example for that is glass. Okay. Now, here refraction of light takes place whenever the light ray is going from one medium to another medium. So, that you can take from rarer to denser or from denser to rarer. Okay. So, when there is a change in the medium takes place, what happens there is, if the light ray is passing from one medium to another medium, like say for example, going from rarer to denser medium here, is rarer is having less density, so that the velocity of light is more here. But once it enter into the denser medium like glass, gradually the velocity of the light decreases. Then what happens there is, due to change in the speed of the light or due to change in the velocity of the light, here there is a change in the path takes place. That change in the path phenomenon or the bending of light, that only we call that as refraction of light. Now, we will see the refraction of light when the light ray is going from a rarer medium like air to a denser medium like glass. As I said, if the light ray is going from one medium to another medium, because of due to the difference in the densities there, the speed of the light is changing. Okay. For example, here now we are considering a medium, a rarer medium like air. Here we are taking a rarer medium like air, and another medium we are taking which is a denser medium, so that we are taking glass. Rarer medium is having less density and denser medium is having more density is present. As it is having less density is present, the speed of light is more in case of rarer medium. And whenever it comes to the denser medium, as it is having more denser, the particles are very much closer to each other, then here the light ray bends because of due to difference in the velocity there. For suppose, if the light ray incident on the surface which is in between air and glass interface, now what happens there is, here at the point of incidence, if you are taking the normal, instead of light ray going in its original path, for suppose if there is no denser medium is present, the light ray has to go straight like this. But as there is a difference in the density is present, then what happens there is, the light ray is changing its path because of due to the velocity is changing. As the velocity changes here, it follows the Fermat's principle, which means light always takes the least possible path. That's why here the light ray is bending, and that too it bends towards the normal, like this. Okay. Then in case of this rarer to denser, as the light ray incident on the denser medium, here because of due to decrease in the speed, because denser medium is more density we have, that's why here the speed of light decreases. As the speed of light decreases, to cover that complete distance in less time, that light ray is bending towards the normal. This bending of light phenomenon, that only we call that as refraction of light. And we already know that if you are taking an incident light ray there, that incident light ray making an angle with the normal, we call that as angle of incidence. And the light ray here, which is the refracted ray, which the light ray going into the another medium, that we call that as refracted ray. This is the refracted ray. This is the refracted ray. This refracted ray, whenever it enters into the another medium like here the denser medium, as the light ray is changing its path, then there is a difference in the angle we are getting. So that here let it be that angle made by the refracted ray with the normal, we call that as angle of refraction, that is. Okay. But if you consider here, if you see here, whenever the light ray is going from rarer to denser, here the angle of incidence is more, whereas angle of refraction is less. And not only that, velocity of light in the medium of rarer, actually it is more when compared to the velocity of light in the denser medium here. Now we will see the same refraction of light, but now the light ray is going from denser to rarer medium. As we already seen in the previous case, as the light ray is going from rarer to denser, here it is going towards the normal here. Now we are taking the light ray is going from a denser medium to a rarer medium like air. So here the light ray is started from a denser medium we are taking like this. Let us suppose down here we are having the denser medium like glass, and the light ray is started from the denser medium like this. Let us suppose this is now our incident light ray. Now, if you are taking the normal, which is the perpendicular line drawn to the point of incidence here, now as the light ray is coming from denser medium where the speed of light is less, and now once it enter into the rarer medium, in case of rarer medium, as the density is less, here the speed of the light is traveling more speed. Means here the light ray which is coming from denser medium, once it enter into the rarer medium, there is an increase in the speed of light. Because of due to that increase in the speed of light, the light ray is taking a path which is deviating away from the normal like this. Okay. Now here if you are taking the angle of incidence, means the angle made by the incident ray with the normal, angle of incidence, and angle made by the refracted ray with the normal, let it be that is R here like this. If you observe here, the angle of incidence is less when compared to the angle of refraction, because the light ray is bending away from the normal. The reason for bending away from the normal is there is an increase in the speed of the light. Okay. So that's why here that bending takes place, and if you observe here the angle of incidence, here it is less than angle of refraction here. And not only that, once the light ray enter into the rarer medium, as the speed is decreasing, here if you see that the incident light ray is having less velocity, whereas whenever it enters into the rarer medium, it is having more velocity is present like this. Okay. This is the refraction takes place whenever the light ray is going from denser to a rarer medium. Now we will see the third case. If the light ray is going from rarer to denser or denser to rarer medium, but the light ray is going along the normal path. If suppose for this surface, now let us suppose the light ray is coming perpendicular to the surface like this. Now once it strikes the surface here, you can take from rarer to denser or denser to rarer. Okay. If the light ray is coming along the normal here, then what happens there is no refraction effect takes place, means there is no change in the path of the light ray. The light ray continues its path. This is the special case we have. Here you can take not only from rarer to denser, even for the case of denser to rarer also same. Like this. If the light ray is coming now from denser medium, once it enter into the rarer medium, here suppose if this is the normal, now the light ray continues its path going in a straight line without any change in the path of the light ray. So, we observe that here in case of this third one, of which if the light ray is going from rarer to denser or denser to rarer, as it is going along the normal, no deviation occurs for the light ray. Now, we will see all the three cases of refraction of light, which is about rarer to denser, denser to rarer and passing through the normal. All the three cases at once we will see now. In the first case, as I said, when the light ray is coming from a rarer medium to a denser medium, here the light ray is bending towards the normal like this. If you observe the angle of incidence and angle of refraction, here angle of incidence is more, whereas angle of refraction is less. And if you see how much is the light ray is deviating from its original path, means this one. This we call that as angle of deviation here. That angle of deviation is given by d is equal to that angle of incidence minus angle of refraction. This is the angle of deviation in the first case, when the light ray is coming from rarer to a denser medium. But once if the light ray is going from denser to rarer medium, for example like this. Now what happens there is the light ray is bending away from the normal here. As it bends away from the normal, here if you compare the angle of incidence and angle of deviation, angle of refraction here, angle of refraction is more, whereas angle of incidence is less, means angle of incidence is less than angle of refraction here. Then if it comes to the case of angle of deviation is the original path of the light ray, incident ray, and how much is the light ray deviating from its original path, that one. This we call that as angle of deviation. Here angle of deviation becomes r minus I like this. Now when come to the next case, if the light ray is passing through the normal like this. Once the light ray passes through the normal, you can take rarer to denser or denser to rarer or and d here. Now the light ray continues its path without any deviation. Means here in this case, angle of incidence is equal to angle of refraction here, and both are equal to 0. And not only that, if you are taking the angle of deviation, there is no deviation takes place, which means the light ray continues its path without any deviation. That is why the angle of deviation is becoming 0. And in the first case here, why the light ray is bending towards the normal is because of due to decrease in the speed. So, velocity decreases. Whereas in case of next one here, as here the light ray is bending away from the normal, in this case the velocity of light increases once it enters from denser to rarer medium. Whereas in the third case it remains same because the light ray is going without any deviation like a straight line. No refraction effect takes place. Mainly in case of refraction, we are having total 2 laws are there. Now, as the light ray is going from one medium to another medium, here the first law tells here the incident ray, all the three lie on the same plane. The incident ray, the normal and the refracted ray, all the three lie on the same plane. That only our first law of refraction. When come to the case of second law, here in case of second law, here as there is a change in the angle is present, means the light ray is deviating from its path. Now we are getting a relation between the angle of incidence and angle of refraction, which is given by Snell. And this is also called as Snell's law here. So according to this Snell's law, this is called Snell's law. According to this Snell's law, whenever the light ray is going from one medium to another medium, if it is changing its path, then the angle of incidence is directly proportional to angle of refraction, or we can also take that as the sine of angle of incidence. The sine of angle of incidence is directly proportional to sine of angle of refraction. This only we call that as Snell's law. If you take out that proportion, if you are taking a proportionality constant, then sine of angle of incidence is equal to a constant k into sine of angle of refraction, that is. Then k is equal to, bring that sine r this side, then it becomes k is equal to sin I by sin r. Here this constant k, we call that as refractive index, a new physical quantity. We call that as refractive index. Okay, it is called refractive index. Refractive index means that is the coefficient of the medium, and it is represented with the letter n. Then finally our Snell's law becomes n is equal to sin I by sin r. N is equal to sin I by sin r. As the light ray is going from one medium to another medium, we can represent that as n 1 to 2 like this. N 1 to 2. This gives you the mathematical form of Snell's law. Now we will see about the coefficient of the medium, which is called the refractive index n. Okay, it is called coefficient of the medium. This refractive index, the coefficient of the medium, we can also take that as it is the ratio to the speed of light. Ratio to the speed of light when it is passing through vacuum, which we are having maximum speed for the light. Speed of light in vacuum to the speed of light in the given medium. Speed of light in the given medium, where the light ray is coming from vacuum going to the medium here, where the refraction takes place. So refractive index is nothing but it is the ratio to the speed of light in the vacuum to the speed of light in the given medium. Then this is called absolute refractive index. Okay, it is called as absolute refractive index. When you are comparing the speed of light with any medium with respect to the vacuum. But if the light ray is going from one medium to another medium, like if you are taking air to glass, glass to water, or water to air, any of that you can take, then how the refractive index changes is it is called as relative refractive index. It is called relative refractive index. Okay, as the light ray is going from one medium to another medium, we represent that as n 1 to 2. Refractive index from one medium to another medium we are taking. Then relative refractive index V is equal to here the speed of light where it is started in the medium 1. So speed of light in the first medium to the speed of light in the second medium. Okay, this is for n 1 to 2, which is called the relative refractive index, speed of light in medium 1 to the speed of light in medium 2. Then n 1 to 2 is equal to V1 by V2, where here the relative refractive index is nothing but we are comparing the refractive index of one medium with respect to the another medium. Then we can write this as n2 by n1 is equal to V1 by V2. If you see the ratio here, both are inversely related, which means that the refractive index and the velocity of the light in that given medium both are inversely proportional to each other, which is a very important relation for our entrance exams. So n, the refractive index of the medium, is inversely proportional to the speed of light in the given medium. N is inversely proportional to the medium. When you are having more refractive index is present, then the velocity or speed of light is less in that medium. If the speed of light is more, which means that the refractive index of the given medium is less. Now, we will see the example for this relative refractive index. For suppose, if the absolute refractive index of water, if you are taking that as 4/3, and whereas the absolute refractive index of glass, let it be that is 3/2. So, N1 represents about the water, and whereas 3/2, N2 is equal to 3/2, it represents about glass. Okay. Now, we are finding as the absolute refractive index of water is 4/3 and absolute refractive index of glass is 3/2. Now, we are writing the relative refractive index, which is if the light ray is coming from water to glass. So, water to glass like this. Okay. Now, here as it is coming to water to glass, then if you compare the refractive index here, then it becomes Ng/Nw, means refractive index of glass, in which medium the light ray is going to enter, to which medium the light ray is started here, Ng/Nw, that is. Then refractive index of glass, which is nothing but N2, this is the water and this is for glass. Then it is N2, which is about 3/2, that is by, and refractive index of water, that is of 4/3, that is. Then it becomes 3/2 into 3/4, that is equal to 9/8. This is the relative refractive index of glass with respect to the water, like this. If it is the same case, if you are taking, if the light ray is started from glass and going to water, okay, means now we are taking the light ray is going from glass to water, okay, glass to water. Then it is represented with refractive index of glass, which is going towards water, or you can also read that as refractive index of water with respect to the glass. We are comparing the water refractive index with respect to the glass here. Then it is equal to now Nw/Ng. Okay. Then it is equal to refractive index of water. We already know that that is of 4/3 by, and refractive index of glass, which is given as 3/2, that is. Then 4/3 into 2/3, which gives you 8/9, that is. If you observe here, if the light ray is going from water to glass, we got the refractive index, which is 9/8, whereas if it is going from glass to water, now we are getting 8/9 here, okay, which means the refractive index from 1 to 2 is equal to the reciprocal of refractive index from N to 1, like this. Now, we will see this relative refractive index or absolute refractive index with respect to the velocity. We will see one example here. For suppose, if you are having the relative refractive index of water, if it is 4/3, okay, n is equal to 4/3. Now, we are finding the velocity of light which is going inside that water. Okay. Let us assume that air is like vacuum, so that the speed of light in the vacuum, we already know that c is equal to 3 into 10⁻⁸ meter/second. Now, this light ray is coming from air and it is entering into the water, which is having a refractive index of 4/3, and we know the formula, the refractive index is equal to the speed of light in vacuum by speed of light in the given medium. As our given medium is water, we are taking speed of light in vacuum to the speed of light in water we are taking. Okay. Then n is equal to, that n value we already know, which is of 4/3, is equal to speed of light in vacuum, that is of 3 into 10⁸ meter/second by speed of light in water, that is of, we do not know, we have to find that velocity, like this. Then if we cross multiply that, then we will get velocity of water, velocity of light in water is equal to 3 into 10⁸ into 3/4, like this. Now, if you calculate that, then speed of light in water is equal to 9/4 into 10⁻⁸ meter per second. That is the speed of light in water when it is going from air to water. Then if you calculate the value, that is of 2.25 into 10⁻⁸ meter per second. Then actual original velocity of the light when it is passing through air, where air is a rarer medium, here the speed of light is 3 into 10⁻⁸ meter per second. But once it enter into the water, where water is a denser medium here, as it is entering into the water, the denser medium, the speed of light is decreased. Okay? So that's why the refractive index here is always inversely proportional to the speed of light. As the refractive index of water is more, so that's why the velocity of light is less in this case. Now we will see another important model in this relative refractive index. You have to find the refractive index of the kerosene with respect to the glass. When compared here, actually kerosene and glass. Kerosene actually it is a rarer medium when compared to the glass, because glass is a solid whereas kerosene it is a liquid. So this is acting like a rarer medium and glass is acting like a denser medium here. And here find the relative refractive index of kerosene with respect to the glass, and we have to compare the velocity of light in both the mediums here. So that the absolute refractive index of water is given 1.5 and the refractive index of kerosene is given 1.4 here. Okay? Then what they are asking is find the refractive index of kerosene. So refractive index of kerosene with respect to the glass, like this, which means the light ray is going from glass towards the kerosene here. Then it becomes Nk/Ng. Okay? Refractive index of kerosene to the refractive index of glass here. That is of refractive index of kerosene given is 1.4 and refractive index of glass, that is of 1.5, which gives you 14/15. Approximately it is equal to 0.92. Okay? So this is the refractive index of kerosene with respect to the glass. Okay? Now we will see if you compare the velocities here. When come to the case of velocity, now we know that absolute refractive index is equal to speed of light in the vacuum to the speed of light in our given medium. So let us suppose if you are taking for the case of kerosene there. Okay? As its refractive index is about 1.4, then speed of light is 3 into 10⁸ meter per second into velocity of light in the kerosene there. Then velocity of light is equal to 3 into 10⁸ by 1.4, okay, which is of meter per second, like this. And if you compare the velocity here, actually if you take 3 by 1.4 means approximately it is equal to 2.2 into 10⁸ meter per second you will get. This is for the case of kerosene. But if you are taking in case of the velocity of light in water, if you are taking, then again as n is equal to c/v, now we will see the velocity of light in glass now. Okay? Then if you are taking the refractive index of the glass, which is equal to the speed of light in the vacuum to the speed of light in our given medium, which is the glass, then velocity of light in that glass is equal to c by the refractive index of the glass here. Then it is equal to 3 into 10⁸ meter per second, which is the speed of light in the vacuum there, and refractive index in glass we already know that that is of 1.5, that is then 1.5 and 2 get cancelled. Then velocity of light in the glass medium is 2 into 10⁸ meter per second, like this. Okay? Then if you observe here, velocity of light in glass, it is 2 into 10⁸ meter per second, whereas velocity of light in kerosene, it is of 2 into 2.21 into 10⁸ meter per second. As the refractive index of kerosene is only 1.4, whereas the refractive index of glass it is equal to 1.5 here. As the refractive index is more, the velocity of the glass is less. Whereas in case of the velocity here, in case of kerosene, as its refractive index is less, which is of 1.4, that is why its velocity is more, which is of 2.21 into 10 power 8 meter per second. Again, it is very clear that the refractive index here, it is inversely proportional to the speed of light in the given medium. N is inversely proportional to V, that is. Now we are seeing the refractive index of the given medium, okay, with respect to Snell's law we will see. According to Snell's law means, we know that Snell's law N12 is equal to sin I by sin R. Let us suppose a light ray is going from one medium to another medium. Let us suppose if the angle of incidence is equal to 60 degrees when it starts from a rarer medium like air. Let us suppose it enter into a denser medium like glass, so that the angle of deviation is less, so that the light ray bends towards the normal, then angle of refraction becomes 30 degrees, that is. Then according to Snell's law, we know that as the light ray is going from one medium to another medium, here it is equal to sin I by sin R, which is sin 60 degrees by sin 30 degrees, that is. Then sin 60 we already know that that is equal to root 3 by 2, whereas sin 30 degrees that is of 1 by 2, that is. Then we got the refractive index of that medium where the light ray is entering, that is equal to root 3, 1.732. Okay. So, this is the refractive index we are getting if the light ray is going from one medium to another medium where the angle of incidence is 60 degrees, where the angle of refraction is 30 degrees here. And in the same way, if you want to calculate the velocity here, then we have to take like this. N12 is equal to sin I by sin R, okay, whereas N12 it is equal to velocity here, if you relate, it is equal to N2 by N1 and it is equal to V1 by V2, that is. Then here N2 by N1 value we got, which is of 1.732 is equal to V1 by V2, like this. So, the ratio of velocities of light, it is also equal to the absolute refractive index here, which is equal to 1.732, that is. Now, we will see the special case in the denser medium, which is called total internal reflection, very, very important one, total internal reflection. In short form, we call it as TIR, total internal reflection, that is. Okay. Now, total internal reflection means actually if the light ray, if it is started from a denser to a rarer medium like this, if the light ray comes from a denser to a rarer medium, according to our Snell's law, here the light ray, here it is bending away from the normal, making the angle of refraction more here when compared to the angle of incidence, like this. Now, if you increase this angle of incidence more, then according to our Snell's law, the angle of refraction also increases here. Like this, gradually if you are increasing the angle of incidence here, as angle of refraction increases and increases, at one particular stage here, the angle of refraction becomes 90 degrees, more bending away from the normal, and finally it is coming perpendicular to the normal, which is about 90 degrees here, like this. Then what happens there is, as angle of refraction here, that is equal to 90 degrees we are getting. Here the angle of incidence, where the angle of refraction here it becomes 90 degrees, that particular angle of incidence we call that as critical angle, that only called as critical angle. Okay, see that again. If you are increasing the angle of incidence more and more at one particular stage, as it is bending away and away from the normal, at one particular stage the light ray here passes along the medium, along the surface, so that the angle of refraction is becoming 90 degrees, which means that here the angle of incidence where the angle of refraction is 90 degrees, that we call that as critical angle. The angle of incidence is called critical angle, that is. Then if you want to find this critical angle, we know that as the refractive index n is equal to sin I by sin R, if the light ray is going from denser to rarer medium, okay, then we know angle of incidence, here it is equal to critical angle and angle of refraction is 90 degrees we are taking. Then refractive index from denser to rarer medium, it becomes sin I, which is sin C, by sin R, which is of 90 degrees, sin 90 degrees, that is. Then refractive index from denser to rarer is equal to sin C by, as sin 90 value is 1 by 1, that is. Then refractive index of rarer medium with respect to denser medium, it is equal to sin C. Okay. Now, if you reverse the equation, reciprocal if you are taking, let us suppose if the light ray instead of going from denser to rarer, now I am comparing the denser medium with respect to the rarer medium, then it becomes reciprocal here, n is equal to 1 by sin C, which means the denser medium we want to get this critical angle is n is equal to 1 by sin C, or you can also write that as sin C is equal to the critical angle, sin C is equal to 1 by refractive index from rarer to denser. Okay. So, as if the angle of refraction is becoming 90 degrees, the angle where the incidence if you are taking, that becomes critical angle, that is. Okay. Now, if you further increase this angle of incidence more than this critical angle, then according to Snell's law, actually the light ray has to show more angle of refraction, but it is already along passing through the surface here. Then in this case, if the angle of incidence is greater than critical angle, then the light ray now comes back into the same medium like this, just like a reflection here. Okay. Now here, whenever the angle of incidence is greater than critical angle, as the light ray is coming back into the same medium, this phenomenon we call that as total internal reflection. Okay. As the light ray is coming back into the same medium, that's why it is called as reflection effect. But this is from refraction case, that's why it is called total internal reflection. Now, we will see a numerical on this critical angle case. Okay, about the total internal reflection. Okay. Here problem is calculate the speed of the light in a medium whose critical angle is 45 degrees. And we already know that critical angle is nothing but whenever if the light ray is going from denser to rarer medium. Now, what happens there is the angle of refraction becomes 90 degrees. That critical angle is nothing but the angle of incidence we are incidenting on the surface here. Okay. As the critical angle is given as 45 degrees, we know that the refractive index of the denser medium becomes 1 by sin C, as we derived that. Then mu is equal to 1 by sin C, where angle of critical angle is given as 45 degrees. So, 1 by sin 45 degrees, that is. Then 1 by, where sin 45 is 1 by root 2, that is. Then it becomes root 2. The refractive index now we got as root 2 here. Okay. But what we need is, here is we have to calculate the speed. As we already know that refractive index mu is equal to speed of light in the given vacuum to the speed of light in the given medium. Our medium is having a refractive index of root 2 is there. Then mu is equal to, which is root 2 is equal to speed of light in the vacuum, which is 3 into 10 power 8 meter per second by, here velocity we do not know in the given medium here. So, let it be that is v, that is. Then we can write v is equal to 3 into 10 power 8 meter per second by root 2. Okay. Then 3 by root 2 approximately will get 2.21 into 10 power 8 meter per second. Okay. Like this, we can get the velocity of light in that given medium as 2.21 into 10 power 8 meter per second. Okay. Now, if you see here, in this case, the refractive index of the given medium, it is given as root 2, which is a denser medium, that is, which is equal to 1.414. From that refractive index, now we are getting the velocity where mu is equal to c by v, that is. Now, we will see another effect of refraction here. Most of the cases, this refraction effect we will see when we are in the rarer medium and the object is present in any denser medium here. Let us suppose here we are considering a beaker or a container here, and the container here we are taking a coin which is placed at the bottom. Now, this coin actually here, as it is at the bottom, now we are filling that container or the beaker with water. Before that, we are having without this water, air medium is present, but now as it is filled with water, here we are getting a denser medium is there. When you are seeing the coin from the outside, from air, as the light rays coming from the coin, actually here they are coming from denser medium here. As they are coming from denser medium, according to our refraction effect, the light rays which are coming from denser to rarer medium, they bend away from the normal. Like this, if this is the normal for this surface, light rays are coming from water which is a denser medium, and the light ray bends away from the normal, like this. So that when you are observing these light rays, then what happens there is the light rays are appears to be coming from a straight line, means like this. The coin, it appears to be raised like this. This effect we call that as apparent depth effect. This is called apparent depth. This is called apparent depth effect, that is. Okay. Whenever if you are taking a coin at the bottom of a beaker, when you are taking that with water there, the coin in the beaker appears to be raised because of due to refraction effect, as we are seeing from the coin through the air, as we are in the air medium, that is. Okay. This shift we call that as normal shift. Okay. Let us suppose if you are taking the original depth, let it be this is OA if you are taking O to A. OA is the original depth if you are taking, and let us suppose this point, let it be that is B, that is. Okay. Then AB is becoming the apparent depth, that is. So, for example, like this, OA, that is the original depth. Okay. Whereas from the surface you can see the coin at OB here. So, that is why OB is becoming the normal shift here, okay, of which OB, which is the apparent depth, that is. Then how much is the shift we are getting is nothing but equal to the shift which is OA, which is the original depth OA, and how much it is raised, that is of AB is raised, means minus OB, which gives you AB. This AB we call that as normal shift. Okay. How much is the coin shift from its position, that only we call that as normal shift, that is. This normal shift actually depends on the medium we are taking. Like here in the case in this one, we are taking that medium as water here. Now here the refractive index of the water mu is equal to, that is of the original depth, or it is also called the real depth. Whereas real depth that we are taking that as OA, whereas apparent depth we are taking that as OB, that is. Okay. So, mu is equal to we got OA by OB, that is. Then refractive index mu is equal to, as it is of OA by OB, which is our normal shift, which is of OA minus OB is given there, that AB gives you the normal shift here. As refractive index mu is equal to, it is of real depth by apparent depth, of which we got that is of OA by OB. So, mu is equal to OA by OB, that is. But what we need is the normal shift. How much is that coin appears to be raised? That normal shift we want. Then AB we got that as OA minus OB, that is. Then if you take here OA common, then 1 minus OB by OA, that is. Okay. Then actually OA by OB is mu, but here we got OB by OA, that is, which means that is equal to OA of 1 minus 1 by mu, that is. Because if mu is equal to OA by OB, then 1 by mu becomes OB by OA, reciprocal to that. Then we got the normal shift finally. AB is equal to OA, where OA is nothing but the original depth here. Okay, that OA into 1 minus refractive index, like this. And in the same way, if you are taking OA, if you want the original depth here, OA is equal to, then it becomes AB by 1 minus 1 by mu, that is, like this. Now finally we got that normal shift, which is of AB is equal to OA into 1 minus 1 by mu, that is. Then if you are taking in case of water in a beaker there, we got that AB as OA is the original depth there, and into 1 minus 1 by mu we got. AB is equal to OA of 1 minus 1 by mu, that is. If suppose if you are replacing this water with any of the glass slab, okay, the same thing now we are taking in case of that water, now we are taking a glass slab here. Means here we are having a surface, below the surface now we are keeping a dot, so that here we are placing a glass slab on that, like this. This ABCD is our glass slab, let it be that is. Then what happens there is, if you are seeing from upwards, gradually it appears to be like the dot appears to be raised. That normal shift only now we got AB is equal to, this is the normal shift. So which means when you are seeing from upwards, here actually the dot appears to be raised. This is our OA, which is the original depth. Let us suppose this is our OB, which is our nothing but this apparent depth, that is, and this is nothing but AB, which is our normal shift. That normal shift we got AB is equal to OA into 1 minus 1 by mu, that is. Then as AB is the normal shift, that is, let it be the distance is D. How much it is raised? Let it be that is D. Whereas OA, that is nothing but the complete glass slab thickness. So that's why that OA we are taking that as T, that is. So T into 1 minus 1 by mu. Or if you want to find the thickness here, the thickness T is equal to D by, which is the normal shift by 1 minus 1 by mu, like this. Now finally we got the thickness of the glass slab T is equal to D by 1 minus 1 by mu, where D is the normal shift we have due to that refraction effect. As T is equal to D by 1 minus 1 by mu, as T is equal to D by 1 minus 1 by mu, then if you cross multiply that, then 1 minus 1 by mu becomes D by T, that is. Then 1 by mu is equal to, bring this D by T this side, of which 1 minus D by T, that is. Okay. Then if you take reciprocal to that, then 1 by mu becomes mu, then it becomes 1 by 1 minus D by T, that is. Okay. Or you can also write that as mu is equal to, if you take LCM, that T come to the numerator, then T by T minus D, that is. This is another formula to find the refractive index of our given glass slab, okay, that is equal to the thickness by the thickness minus the normal shift. That normal shift is nothing but our apparent depth, that is, okay, which is T by T minus D. Now we will see a small problem on this normal shift. Here it is given that a small pin fixed on a tabletop is viewed from the above from a distance 15 centimeters. Let us suppose here if you are taking a surface, on this surface now we are taking a pin, okay, and this pin actually we are seeing above from that at a distance, let us suppose given as 50 centimeters, that is, okay. Now, given that by what distance would the pin appears to be raised, which is our nothing but the normal shift, okay, appears to be raised, that is, when viewed from the same point through a 15 centimeters thick glass slab, that is, okay. So, that the original thickness of the glass slab is already given. Let us suppose this is the glass slab, so that the thickness of the glass slab is given, which is of 15 centimeters is given there. And we also given that the refractive index of the given glass slab is about 1.5, that is, okay. And now we already know that D is equal to where the normal shift, okay, it is equal to T of 1 minus 1 by mu, that is, where D is the normal shift, T is the thickness of the glass slab, and mu is the refractive index of the medium, which is the glass we are taking now, okay. As D is equal to then the thickness already given, that is of 15 centimeters, of 1 minus refractive index, where the refractive index of the glass slab is given as 1.5, that is, okay, 15 of 1 minus 1.5, that is. Then D is equal to 15 of, here if we take the LCM 1.5 and here it becomes 0.5, that is, as it is of 1.5 minus 1, that is. Then finally it becomes D is equal to 15 of 5 by 15, then 15 get cancelled. Then finally we got D is equal to how much it appears to be raised is 5 centimeters. Okay. So, means actually viewed without the glass, we can see that from 50 centimeters, but once the glass slab is placed, the same point, that pin appears to be raised by 5 centimeters, which means that from the top point where we are seeing that it appears to be raised by 5 means the distance now it is becoming only 45 centimeters. This is the refraction effect. We call that as apparent depth effect. This is. Now, the apparent depth of the coin lying at the bottom of the tank is measured by a microscope is 9 centimeters, that is. So, which means here if you are placing a coin at the bottom of the beaker and once you are seeing that through a microscope here from the top, now here it appears to be raised by 9 centimeters is given, which means the apparent depth of the coin appears to be given that as 9 centimeters, that is, like this. Now, what is the refractive index of the water? As water is a denser medium, that is why we are getting that refractive index refraction effect, that is, which is of 9 centimeters normal shift we got. Then we know that the refractive index mu is equal to real depth by apparent depth, that is. As it is of real depth by apparent depth, then real depth, that is of original, it is of 12 centimeters. Whereas, if you are taking here the apparent depth, it becomes 9 centimeters, that is. Then 12 by 9, which is of 4 by 3, that is approximately 1.33. So, that is the refractive index of the water which is taken into that container, that is. And here how much is the position, because of due to that coin appears to be raised there. Here given that if water is replaced with another liquid of refractive index of 1.5 to the same height, now we are changing the refractive index here. So, once you are changing, this is for the case of water, now we are taking another liquid here, let it be that liquid is L. So, refractive index of that liquid given as 1.5 here, okay, is equal to the real depth here, as it is filled to the same height. Now, the real depth again it becomes 12 centimeters only, that is. Then we need to find the apparent depth here. Apparent depth we have to find here. Let it be that apparent depth is x. Then x is equal to, if you cross multiply that, 12 by 1.5. 12 by 1.5 means we can write that as 3 by 2. Then it becomes 8 centimeters, like this. Okay. But if you are taking in case of water, which is having a refractive index of 1.33, the apparent depth is 9 centimeters here. But once if you are taking the refractive index of the liquid, which is 1.5, then the apparent depth is becoming 8 centimeters here. Then how much is the shift here we required? There is actually here original depth is 12, here we got 8, then 12 minus 8, which is of, that is the normal shift required. So this is what they are asking. Here the by what distance would the microscope have to be moved to focus the coin again? Means here we are getting a problem, instead of taking that original depth of 12 centimeters, here it appears to be at 8 centimeters. So we have to adjust the distance here. D is equal to, original is 12 centimeters, but it appears to be raised by 8 centimeters. Then how much is the normal shift required? There it is of 4 centimeters, that is. Whereas when you are taking for the case of water, as the apparent depth it is about 9 centimeters, the shift required there is, in case of water, it is of 12 minus 9, only 3 centimeters is what required. Whereas in case of liquid, when you are using, then density of the liquid, here the distance we have to move inside the liquid, it is of 12 minus 8, 4 centimeters we have to move there. If you observe that, as the refractive index of water is less when compared to the refractive index of liquid, because water refractive index we got only 1.33, whereas the refractive index of liquid we got 1.5. As the refractive index is more, the shift required is also here it is more, because if the refractive index increases, gradually the refraction effect also increases, so that the coin appears to be more raised. That's why here the normal shift is 4 centimeters, whereas in case when you are using the water, it is only 3 centimeters is there. Okay. So from this it is very clear that once if you are having increasing the refractive index of the medium there, gradually the normal shift also gradually increases, which means the apparent depth is also increasing. So that in the first case we seen, in case of that total internal reflection, we got mu is equal to 1 by sin c, that is. Okay. Which means the refractive index is more, then sin c value is less, as this is related inversely proportional to each other. Okay. So the refractive index mu is inversely proportional to the critical angle here. Okay. So if the refractive index is more, then the critical angle required is less. And in the same way, if the refractive index is less for the medium, then the critical angle will be more. Best example for that is in case of diamond, that is, diamond actually it is having a refractive index of 2.5 approximately. Okay. Diamond is having a refractive index of very high refractive index 2.5, that is. So that's why the refractive index of diamond is 2.5, so that its critical angle is very less only required. This is the reason for diamond showing the special effect of here like sparkling. Let us suppose if you are taking a diamond, okay, like this, which is a denser medium having a refractive index of mu is equal to 2.5. Because of due to refraction, as the light ray bends towards the normal here like this, after refraction is over, as the refractive index is 2.5 more we have, the critical angle is very less for that, so that its critical angle becomes as mu is equal to 1 by sin c, then sin c is equal to 1 by mu, where mu is 1 by 2.5, then c is equal to sin inverse 1 by 2.5, that is. So for any angle of incidence here, it shows the total internal reflection effect, that is. Coming to the total internal reflect means the light ray is coming back into the same denser medium and again incident on the another surface here, of which again here the angle of incidence is greater than the critical angle. Again it takes going on the total internal reflection effect like this. Again it takes total internal reflection, so that the light ray is undergoing number of multiple total internal reflections inside like this. This causes the sparkling of diamond because of due to the refractive index is more and the critical angle value is less for the case of diamond here. That is the reason.